Our universe is vast. This vast universe is filled with strange and terrifying places, but the place we're talking about today goes beyond all limits. This place has such an immense gravitational pull that if you ever find yourself near it, there's no way to escape even if you move at the fastest speed in the universe, which is the speed of light. This place can literally freeze and stop time. At this place, all the laws of physics collapse. It grabs those laws and throws them in the trash. And I probably don't need to tell you what this place is. It's the black hole. If you're one of the 2 or 3 people on Earth who don't know what a black hole is, let me quickly explain. In short, a black hole is a space object with extremely strong gravity, so strong, in fact, that it can trap even light. And since light is the fastest thing in the universe, that means anything else that gets too close to the black hole is doomed. It won't escape either. Now you might wonder, how can something like that even exist? And how does it do all these weird things? To understand what a black hole is, we first need a quick review of gravity and how it works. Imagine you're standing on Earth and you throw a ball upward. The ball will keep going up for a while, but eventually, it will come back down because of Earth's gravity. Even if you throw the ball harder, it'll go higher, but gravity will still bring it back down. That's because you're not throwing it fast enough. Now imagine you had a super powerful cannon and fired the ball upwards at an extremely high speed. If the speed is high enough, gravity won't be able to pull it back, the ball would escape Earth's gravity completely. That specific speed is what we call escape velocity. It's the speed something needs to escape the gravitational pull of a planet or any other body. For Earth, escape velocity is about 11.2 kilometers per s. Of course, this number changes depending on where you are, because gravity differs from place to place. If you go to a place with less mass, like the moon, the escape velocity drops. On the moon, you'd only need 2.4 kilometers per s. But if you go to a much more massive object like the sun, the escape velocity shoots up to about 615 kilometers per s. So the more massive the object, the higher the escape velocity you need. But now we hit a huge problem. Imagine we go to a certain space object whose mass and gravity are absolutely massive, and we try to do the same ball experiment. We calculate the speed needed to escape this object's gravity and find that we'd need a speed of over 300,000 kilometers per s, which is faster than the speed of light. But since nothing can go faster than light, that means nothing, not even light, can escape this object. So here's the good news and bad news. Bad news. We're trapped. There's no way to escape this object. Good news, congratulations, what we just found is a black hole. That's actually the first idea or concept ever proposed about black holes. A star so massive that its escape velocity exceeds the speed of light. This idea isn't new. It was first proposed back in the 18th century by a scientist named John Michel. He suggested that maybe there are stars in the universe with such massive gravity that even the light they emit gets pulled back in, and so no light escapes. These stars would be invisible to us. We wouldn't be able to see them even if they exist. So he called them dark stars. Now I can hear someone being clever and saying, "Hey, Rushdie, that's wrong. We learned in school that for any 2 objects to attract each other, both need to have mass. And light doesn't have mass. It's massless." You're right, partially. That's actually the reason Michel eventually abandoned his idea. Because according to Newton's theory, light was considered to be particles, which means it could have mass and be affected by gravity. But later, people started believing that light is actually a wave, specifically an electromagnetic wave, not particles. So how could gravity affect a wave? That left Michel confused, and he eventually gave up on the idea. And so, the concept of dark stars, or black holes, stayed buried for a long time, until the early 20th century, when a new theory revived the idea. Even though the concept of a massive object that can trap light was fascinating, Newtonian physics had a major obstacle. According to Newton's laws, if an object has no mass, then it cannot be affected by gravity. Since light is massless, this seemed impossible. But then came 1915, and everything changed. That year, a brand new theory of gravity came out, one that rewrote Newton's laws completely. That theory was general relativity. In the early 20th century, Albert Einstein noticed that Newton's laws were starting to fall apart. Not on Earth, where things worked fine, but in extreme gravitational conditions, like the orbits of planets around the sun. Einstein worked to come up with a new theory that fixed those issues, and that led to general relativity. Einstein said, "Newton's concept of gravity is wrong. Newton thought gravity was a mysterious force that pulls any two objects with mass toward each other. But Einstein disagreed. He said, "With all due respect, sir, that's not how it works. Gravity isn't a force at all. Gravity is the curvature of space-time itself, the fabric of the universe. Massive objects like the sun bend space-time around them, and that curvature tells planets how to move. Imagine I draw a straight line for you and ask you to walk along it, but then I grab the line and bend it. You're going to follow the new curved path. That's exactly what happens with planets. Now here's the interesting part. If the object moving has mass, like a planet, then it also bends space-time, adding to the curvature and increasing the gravity. But even if the object doesn't have mass, like light, it still has to move through the curved space-time created by the massive object. So yes, light is affected by gravity. So can we actually have a star so massive it can trap light? The answer is yes. The problem was no longer whether light could be affected by gravity. That was solved. But now, the new challenge was whether such a star could actually exist and still be stable. But the idea itself? Totally valid now. And just a few months after Einstein published his theory, a German scientist named Karl Schwarzschild came along and solved the equations of general relativity for a very specific case, the gravitational field around a spherical object. But there was a problem. The solution he found predicted infinite curvature in space-time. That means infinite gravity. Wait, infinite gravity? That must mean an insanely massive object, right? Surprisingly, no. His equations didn't say the mass was enormous. They said the size of the object was nearly zero. Basically, it had no volume at all. Want to know how he reached that conclusion? There's a detailed video for that on the channel, just for the members. Still, that's bizarre. How can something's size affect its gravity? Here's the missing piece we ignored earlier: distance. When we talked about gravity, we kept saying the more mass, the stronger the gravity. That's true, but we were ignoring how distance affects gravity. Gravity weakens the farther you get from the object. That's why astronauts in orbit feel less gravity than we do on Earth. They're farther from Earth's center. Now imagine the size of the Earth shrinks, but the mass stays the same. That means we can get closer to its center, and gravity becomes stronger. And if the Earth's size keeps shrinking, we can get even closer, and gravity keeps increasing. Now imagine a body with zero volume. We could theoretically get infinitely close to it. And at that point, gravity would become infinite. That means we were looking in the wrong place all along. We thought we needed a star with insanely huge mass, but maybe we just need a very small volume instead. But now we hit another problem. Morning sunshine, size of zero, really? That was basically the reaction from scientists, including Einstein himself. They rejected the idea of an object with zero volume. Physics, especially a rule called Pauli's exclusion principle, says you can't just take, say, two electrons and squeeze them into the exact same place. No two identical particles can occupy the same space. And here you are telling me that we're taking something like the sun, all its electrons and protons, and shoving them into a single point? That's impossible, they said. The densest objects we knew of back then were white dwarfs, the remnants of dying stars like our sun. When a star collapses, it shrinks, but stops at a certain size. Why? Because of Pauli's exclusion principle. It keeps matter from collapsing infinitely. That principle backed the scientists' argument. No such thing as an object collapsing to zero size. They said, if such an object existed, we'd have seen something denser than a white dwarf, and we haven't. So stop dreaming about black holes. So it felt like every time we got close to proving black holes exist, hope disappeared again. But no, our story doesn't end here. Hope never truly dies, and scientists never stop asking questions. But since this topic is getting long, we'll stop the video here. As for how hope returns, how scientists managed to prove the existence of black holes, how they were able to detect them, and even how they were able to photograph them. All of that, we'll explain in the next video. So that's it for today's video. If you've made it this far, I love you. Let me know in the comments if you watched to the end. Don't forget to subscribe so you don't miss part 2 and upcoming videos. And like this video to support us to keep making more content like this. If you want to actively support the channel and help fund these videos, you can become a member using the join button next to the subscribe button. That gives you access to exclusive videos, early access to future uploads, and helps me dedicate more time to creating content. That's it. Thanks again for watching all the way to the end. Wait for the next video. Peace out.